Good morning, everyone. So we are back to electromagnetic induction. So I'll start off with the experiment of Michael Faraday. Do you remember the experiment? Okay. Yes. Coil magnet experiment. You take a coil like a wire, and then wire is wound over a pipe. Okay. And you connect a galvanometer to this. What is a galvanometer? Galvanometer is a device to show the current. That always shows the current. Okay. There are many electrical equipments like ammeter. Ammeter shows the amount of current. Ammeter shows how much of current is flowing. Voltmeter shows. Voltmeter shows the voltage. Ammeter shows the current. And what about galvanometer? Galvanometer shows if there is any current or not. Okay. If a current flows, galvanometer shows deflection. The needle shows deflection. Got it? So galvanometer is basically an output device. You see the deflection, you understand what? There is a current flowing. Correct. And you connect a galvanometer to this. And then what? You are introducing a magnet into this. This is north pole and south pole. Okay. So I'll tell you the context one more time. We have a coil. The coil is wound over a pipe. Okay, that is also called a solenoid. Okay, and then what? You are introducing a magnet into this magnet. Okay, and you're going to see what now? The magnet has a lot of lines. These lines are called what? Magnetic field lines. But as someone who learns physics, I would call it flux lines. Okay, flux lines. For a common man, this is like few lines which you can't see. Got it? But for someone who learns physics, these are actually tool to represent a magnetic field. Got it? Magnetic field lines are drawn from where to where? Turning within a north pole to south pole. All the lines are drawn from north pole to south pole. You learned this even in class 10, right? Stay present, please. Okay, so all these lines are what? These lines are together called flux lines. And what's happening now? When you put this magnet into the coil, suddenly the needle shows a deflection. Got it? But and on the other hand, when you take it out, what happens? There is another deflection, but in the opposite direction. Got it? I repeat, I put the magnet in, then what? Suddenly I see a deflection, momentary deflection. The needle goes to this side and comes back. When you take it out, the needle goes to, tell me, other side and comes back. Got it? So what would you see here? A deflection. When did you see this? When a magnet was moved. Correct. And what is our conclusion? There is a current flowing. Current flowing, right? Why does the current flow? An EMF is generated. EMF means voltage. Correct. Why is the voltage generated? The answer was given by Michael Faraday. Michael Faraday said that a flux change. Flux is changing here. Flux change. Flux change causes an EMF. Flux change. How does the flux change here? It is obvious. When you put it in, these lines are being cut. Correct. Those lines are being cut. Or we would say intercepted. Those lines are intercepted. We say that the lines are intercepted, but Faraday prefers to call it flux change. Got it? Both are the same thing. Actually, we would call them by different names. We call them the lines being cut. Correct. But according to Faraday, it is called flux change. Got it? So whenever the flux changes, an EMF is generated. This is the summary of the chapter. The whole chapter can be summarized in a single sentence. That would be this sentence. Flux change causes EMF. Got it? This phenomenon is called electromagnetic induction. And we even learned the equation for this. EMF is given by minus d phi by dt. D by dt means rate of change. Rate of change of flux. How much of flux is changing per second? Got it? I repeat one more time. Rate of change of flux. Flux changing per second. The amount of flux changing per second. Got it? So this is the introduction. I repeat this one more time. This is all about electromagnetic induction. In fact, the large scale power generation you see is actually based on this principle. Understood? I've told you many times in Niagara Falls, water is stored in a reservoir. Water comes down through a pipe called penstock. Penstock, this is the Niagara Falls Dam. Alright. Water comes down through a pipe. The pipe hits a turbine. Water hits a turbine. Huge fan, that is called turbine. The turbine rotates, which is like continuous movement of a magnet. Got it? Instead of putting the magnet into and out of the coil, they'll make it rotate. Got it? You'll have the same effect. Got it? So electricity is generated. Across the world, the same principle is used to generate electricity. Got it? Which is called electromagnetic induction. Okay? It is such a revolutionary invention. You know, without this, nothing would have been possible now. Understood? The kind of development we have. Right? This is actually invention of electricity that we are talking about. Got it? And this was done in 1820. Alright, by Michael Faraday. Okay, so basically a flux change creates an EMF. I repeat, Faraday, this is Faraday's coil magnet experiment. According to the experiment, the coil has a galvanometer attached to it, and whenever the magnet goes into the coil or comes out of the coil, the needle shows deflection. That means there is a current flowing. Okay, why is the current flowing? Because there is an EMF developed. Why is the EMF developed? Because the flux is changing. Why does the flux change? Because the lines are cut. Why are the lines cut? Say something. Because you are putting the magnet in. Right? So let us go backwards now. You are putting the magnet. The lines are being cut, which is called flux change, which creates an EMF, which in turn creates a current, electric current. Got it? So basically the end result is generation of a current, EMF. EMF means voltage. Correct? For current by way of change of flux. So flux change creates an EMF. And what is the equation for EMF? EMF is given by minus d phi by dt. Negative rate of change of flux. That is the first point. Now I'll tell you something. There is something called self-induction. Self-induction. I told you about electromagnetic induction, and it is further classified into two: self-induction and mutual induction. I'll tell you one by one. Look at this, look at this. Right. I have a coil. Look at this, I have a coil. This is also called a, tell me, Leslie. This is also called a solenoid. Solenoid, right? The coil is also called a solenoid. If you take a pipe and if you wind a coil, that's got another name, solenoid. Okay. And you connect a cell to this cell and a switch to this. Okay. Now you tell me, what happens when you switch it on? What happens? Current begins to flow, right? Correct? Yeah. Current begins to flow, right? Current flows from positive terminal, right? But this current does not come abruptly. We would like to think that the current shows a rapid growth, but the current in fact takes time to grow like this. Got it? The time is actually, it is over a time that the current grows to maximum value. Got it? So when you switch it on, the current slowly increases. Slowly, current increases. Got it? Got it? So current increases. What happens when current increases? The magnetic field inside will increase. Inside the solenoid, there is a magnetic field. There is a magnetic field. Inside a solenoid, there is a magnetic field, right? Yes. I'll show you later. Okay, inside a solenoid, there is a magnetic field. Magnetic field increases. Magnetic field increases means flux increases. The technical term is flux. It's nothing but magnetic field itself. Okay, flux increases. So when you switch it on, tell me, when you switch it on, the current increases, magnetic field increases, flux increases. Similarly, when you switch it off, tell me, current decreases. Current decreases to become zero, right? Magnetic field decreases, flux decreases. All right. Either way, the flux change is happening, right? Flux change is happening, right? So both of them will result in EMF. This phenomenon is called self-induction. Self-induction. It happens on its own, right? Self-induction, only one coil. And the phenomenon is called self-induction. The EMF is called self-induced EMF. Self-induced EMF. Got it? Self. It is actually induction itself, electromagnetic induction itself. Okay, I'll show you later. Anyway, this is electromagnetic induction. Again, flux change causes EMF. Flux change causes EMF. Say it again. Flux change causes EMF. Always. Okay. Now here what's happening? Look at this. I'm switching the circuit on. The current increases. So the field increases. Flux increases. Similar way, when you switch it off, current keeps decaying. Current keeps dying, right? Then what? Eventually, current becomes zero. So field decreases, flux decreases, EMF is developed, right? And this phenomenon is called self-induction. Okay, self-induction. This phenomenon is called self-induction, and the EMF is called self-induced EMF. Now here comes my question. Imagine I have two coils. Look at this. I have two coils. One coil like this, to which I connect a cell and a switch. Okay, this is going to be called primary. Primary, right? Okay, and close to it, I'm keeping another coil called secondary, to which I connect a galvanometer. Got it? And what are you going to do now? You're going to switch this on, the primary. Primary is switched on, right? Tell me what happens now. When primary is switched on, primary current increases. Just like all times, right? Current increases. Tell me. Current increases means what? Primary field increases. Correct. Primary field increases means primary flux increases. Look at this. Primary flux. This is primary flux. But a part of it is shared to secondary, because they are sitting in the vicinity of each other. Got it? They are sitting close to each other. If they are far apart, the flux transfer will be less. Understood? But if they are very close, in fact, they are wound over each other, so as to have maximum flux transfer. That's called coaxial winding. I'll come back to that. Okay. Anyway, this is what it is. When you switch it on, primary current increases. So primary field increases, primary flux increases, automatically secondary flux also increases. What happens when you switch it off? Primary current decreases, primary field decreases, primary flux decreases, secondary flux also decreases. Either way, there is change of flux, right? And what did Faraday tell you? Change of flux should cause an EMF, right? So there is an EMF, and this phenomenon is called mutual induction, and the EMF is called mutual induced EMF. Got it? Have you seen the application of this before? Have you seen a wireless charger? Yeah. Latest Samsung phones and iPhones have like wireless chargers, right? You put your phone on the charging pad and the phone automatically gets charged, right? What is it? It's in fact mutual induction. Where is the primary coil? It's inside the charging pad. It has like, can you just one second. That's it. This is the secondary coil. Look at this. That is a coil, okay? That is a coil, secondary coil, okay? Right. So this is secondary coil, and you're putting it on top of a charging pad, okay? And inside the charging pad, there is another coil similar to this. All right. That will be primary coil, and primary coil will have a changing current. Got it. So changing field. So changing flux, which will induce a changing flux here, which will charge the battery. Understood? And what are scientists trying to do now? They are trying to increase the distance. Now you have to keep it on top of the pad, right? And they are trying to increase the distance. And in the near future, you will see something like this. There will be pots, small boxes. You can just go close to it, stay there. Your battery will automatically get charged. You can keep the phone in your pocket. They are trying to increase the distance, and that's in fact called wirelessity, wireless electricity. I told the class once. Listen, scientists at MIT, they have already been successful in transmitting electricity through air over a distance of 131 meters. All right. So in future, you can take electricity out of thin air, right? Just take electricity down. You can just use the Wi-Fi. No? It's the same way you use Wi-Fi. You can get electricity like that. Nowadays, we have electricity how? Underground cables. Back in India, we have overhead cables. No? You can see the cables. But in developed countries like Qatar, they have all the cables underground. Got it. Now electricity is carried by cables. But in the near future, you will see electricity through air. Got it? So even MIT researchers have done another thing. From Wi-Fi signals are captured and that is converted into electricity. All right, I'll show you. Okay. Another thing is what you call. Have you seen an induction cooktop? Induction cooker. You have at home induction cooker, no? You put a pan on top of it, and then you put the food articles inside. That gets automatically cooked. So I think I took it here. Just give me a second. Just give me a second. This is it. Look at this. Can you see this? Can you see this? Yeah, I'll answer that question, Andrew. Okay, so this is the span you place the secondary coil. Where is the primary coil? It is under the cooktop. When you're home, open the backside of the cooktop. Okay, you can see the coils inside. And inside the coil, the current is continuously changing. Current is continuously changing. That creates a changing magnetic field, changing flux, which creates a current on the pan, which actually causes heating up. But I still can't figure out why the pan doesn't get heated up, sides of the pan. If you try the induction cooktop, you can see this. Only the bottom will get heated up very quick. I don't know why. Maybe because the bottom is made up of copper. Copper heats up fast. But sides won't. If you touch sides, you won't have any heating. Understood? Only the bottom gets heated up very quick. Induction cooktop was on. But Chinese have actually invented clay-based induction cooktops. I don't know how. Anyway, this is like induction. When you purchase the pan, it will be written on it. It is induction compatible. Induction cooktop. It can be used in induction cooktop. The bottom has to be induction cooker compatible. Understood? Alright, so that is the working of induction cooker. So this is mutual induction, and I'll show you something. Look at this. I think I've shown already. This is the mutual induction I was talking about. Look at this. I've seen this already, but anyway. Look at this. This is the primary coil, okay, which has a changing field. And where is secondary coil? It's under the bulb. You can't see it. So tiny. Okay. See what happens when you put it in. Look at that. The bulb glows, right? Okay. I take it out. It's not there. Right. This is same thing again. Same thing. Mutual induction. Look at this. This secondary coil connected to a bulb. That's primary. Bulb automatically. Right. So another one is, this is another beautiful demonstration of mutual induction. We have two coils here side by side. See this? This is primary. You have seen this already. This is primary coil to which you connect the radio. Okay. This is secondary coil which is connected to a speaker. Speaker is the output device. All right. And when music is played on the radio, there is an EMF, varying EMF. That is, sound is converted to electrical pulses. Got it? There will be an EMF developed on the secondary coil, which means you will hear the sound on the output device speaker. See this? When they come closer, what do you expect? There will be more flux transfer. Correct? See, when the coils are closer, the flux transfer will be more and the sound will be more clear. Correct? And when the coils are perpendicular, you won't hear anything. I'll tell you why later. Okay, perpendicular, there won't be flux transfer. Okay, just see this. See this? Primary coil. That is secondary. Move it away, it's less. Why? Because less flux transfer, right? There is a previous question based on the concept. I'll tell you. When they are perpendicular, that is a question. There is no flux transfer. I'll tell you why. Because I have no sound, right? And this is what I was talking about, the wireless electricity.
Wi-Fi signals could one day be converted into electricity to power electronic devices without batteries, thanks to a new innovative technology. MIT researchers created a fully flexible rectenna that captures Wi-Fi's electromagnetic waves and converts them into electricity using a radio antenna and a 2D semiconductor. The semiconductor turns the AC signal into DC voltage, and it could be used to develop battery-free devices that passively power themselves using Wi-Fi signals. This includes smart pills that could be swallowed by patients and stream data back to computers, and even bridges, highways, and buildings that could have self-charging capabilities. The flexibility of MIT's device allows it to cover very large areas, making it possible to power the billions of smart devices, leading to the smart cities often displayed in science fiction. Another team used nanoscale devices that can generate and detect microwave signals to convert Wi-Fi signals into a direct current voltage that charges a capacitor. By charging the capacitor for 5 seconds, enough energy can be stored to power a 1.6 volt LED for 1 minute. Scientists aim to expand the technology for use in battery-free electronics and neuromorphic computing systems.
Okay, hope it's clear now. Is it clear? Shall we just have an introduction? Right, start writing. Okay, right, recap. You can write whenever the magnet moves into or out of the coil, galvanometer shock deflection. Whenever the magnet goes into or comes out of a coil, galvanometer shock deflection. Draw the figure. These are the field lines. So what's happening here? The lines are being cut, right? The lines are being intersected, right? The lines undergo a change. Correct. That is why all these things happen, right? Have you seen the field lines? Have you seen the field lines before? Look at this. I think I showed this once. This is how field lines are.
Just found this little demonstration tucked away in the back shelf here. It's always fun when I do that. And I think that you're all going to enjoy it. It's pretty cool.
These are iron filings.
This is a really cool way of visualizing three-dimensional.
You will introduce a magnet into this. You can see that
suspended in oil.
where the lines are to be
this magnet into the middle. And watch the magic happen. You can see all of the little filings are lining up. So they're going from north to south. That's how magnetic field lines point. And now you can see in three-dimensional space. But what is this one invisible magnetic field?
The concentration is around the pole. So you can see the lines here, right?
Pretty darn.
Can you see this? Right. Those are how field lines are drawn. Alright, so you can start writing like this. Whenever the magnet moves into or out of the coil, solenoid should be connected to battery, Praveen. No battery is needed here because you are generating electricity here using the movement of the magnet. Okay. Whenever the magnet goes into or comes out of the coil, whenever the magnet goes into or comes out of the coil, no. Here also an EMF is generated that will oppose the cause by Lenz's law. That will oppose the cause, Praveen. Because when the north pole comes in, the north pole will be repelled. Who repels it? The EMF developed will repel it. I'll tell you, I'll come back to that later. Okay, right. So look at this. Whenever the magnet moves into, so what is our conclusion? Write the conclusion. Not our conclusion, Faraday's conclusion. Okay, write the conclusion. What is the conclusion? Nobody saw. Tell me. Flux change. Flux change causes or flux change creates EMF. That is what we're going to learn in this chapter. The whole chapter. Flux change causes EMF. But the presence of flux alone is not sufficient. Flux should be changing. Do you see the word change here? Changing flux is essential. Understood? How did the flux change here? By moving the magnet. How did the flux change here? Say something by moving the magnet, the lines are cut. The lines are cut. I said 7 times so far. The lines are cut. Got it? So by moving the magnet, you are changing the flux. Change of flux creates EMF. Got it? Got it? This is electromagnetic induction. Got it? And this is called, you can write electromagnetic induction. Electromagnetic induction. Right? This is called, this phenomenon is called electromagnetic induction. This phenomenon is called electromagnetic induction. Okay. Electromagnetic induction. Okay. And electromagnetic induction is further classified into two. What are they? Self-induction and mutual induction. If you don't answer, I'm going to ask you to write 100 times. Okay. Self-induction and mutual induction. Self-induction and mutual induction. Okay. So let us write this first. Self-induction. Write the name. Self-induction. Self-induction. From the name itself, it is clear. Self. Self means on its own. Right. Self-induction. All of you online, could you please tell me if you understood or not? Everyone, I'm watching. Okay. All right. So self-induction. Draw the figure. What is this called again? Solid. This is called solid now. Yes. Okay. Right. Connect a cell now. This is a switch. Okay. A cell and a switch. Okay. Right. Cell and a switch. Then what? You're going to do what? You're going to switch it on. Okay. You can write a coil is connected to a cell and a switch. A coil is connected to a cell and a switch. Okay. Now, tell me, Aryan, what are you going to do? On, switching on, what happens? Current will start increasing. You expect the current to become maximum all of a sudden, but that doesn't happen. Current grows over a time. Got it? Current takes a time to grow. Got it? Okay, that's called transient growth, but that's not there in your syllabus. Anyway, switched on, current increases. Right? Current increases. Current flowing through it keeps increasing. Then magnetic field increases. Magnetic field increases means flux increases. Switching on. What's happening now? Switching off. What's happening? Current decreases. So magnetic field also decreases. Flux also decreases. Okay. So you see a change in flux here, right? Yes. Right. Tell me, Aneja, what happens now? Change in flux should result in EMF. Yes, very good. Generation of EMF. EMF. EMF stands for electromotive force. Electromotive force. Okay. Electromotive force. Voltage. Now, right. When the flux linked with a coil, we are going to write the definition. When the flux linked with a coil changes, and EMF is developed in the coil. This phenomenon is called self-induction. EMF is called self-induced EMF. Now write mutual induction. Now mutual induction. Right, it's mutual induction. Right. Mutual induction, right? This self and mutual, you know the difference, right? Self means only one. Mutual means mutual. The term mutual comes when you have two guys together, right? Mutual interaction, right? Mutual means between, right? Okay, so you can draw this. We have a pair of coils this time. This is called primary coil. Primary coil is connected to cell and a switch. This is called secondary coil, which is connected to a galvanometer. Okay, primary and secondary. Primary and secondary. Okay, so what are you going to do now? You're going to switch the primary on now, right? Primary on. So they are kept very close. In fact, we will keep them together, right? I'll show you the actual device data where they wind one on the other. There are transformers.
So your total number of coils need to be equal.
No. It depends on what you want, right? There is a ratio called turns ratio. You can keep it any number as per the requirement. Okay. If you use this thing every day on an everyday basis, there is something called a transformer which cuts down the voltage. Because the supply from Karama is 220 volts. 220. But your mobile phone is working on what? You open the phone, you can see 5.3 volts written on it. Battery is on 5.3. So you have to cut it down to 5.3. You use a transformer. Mobile phone charger has it. Understood? The AC, AC has a voltage stabilizer. Here you can't see because it is integrated, it is kept inside. Back in India, you can see a separate piece.
Yeah.
Next to AC.
Next to AC. That's called a stabilizer. That's a voltage changer. Got it. In India, you have voltage fluctuation also. Voltage fluctuation also. Sometimes the required voltage is 220. Sometimes it goes as low as like 140. It might go up to say 330 volts. Understood? So that might actually damage the device. But in Qatar, we don't have fluctuations, so we don't in fact need the stabilizer here. But still, they keep it inside again. All right. Even the refrigerators have it integrated piece now. All right. Everywhere we use this, even inside your laptop, you cut down the voltage. You don't give the voltage as such. That will blow the laptop. Got it. All right. Okay. So just write this mutual induction. Okay. So you can write when the switch in the primary is made on, you are switching it on this time. When the switch in the primary is made on, who is on this idea? iPhone 16. Yes, spelling is wrong. It's not grow. It's grow. Yeah, make it clear. Okay, switching on. When the switch is made on, right. When the switch is made on, somebody has written iPhone grow. IP increases, primary current increases. Okay, when the switch is made on, primary current increases.
Yeah.
Primary current increases. Okay, primary current increases means what? Primary field increases, right? When the current in the primary increases, I'll answer that question, okay? I saw the question, I'll answer that question. Primary current increases, primary field increases, primary flux increases. As a common man, I would call it field, and somebody who learns physics would call it flux. Okay, so both are the same thing, in fact. Okay, field increases, flux increases, flux in the secondary also increases. Look at this. I switch it on, primary current increases, primary field increases, primary flux increases, secondary flux increases. Tell me about switching off. Number 2, switching on. Switching on. The current decreases, primary current decreases, primary field decreases, primary flux decreases, secondary flux decreases. Both ways you have what? You have like a change to flux, which creates an EMF, isn't it? An EMF is, EMF is produced. Okay, so you can write when flux in the primary changes, primary coil changes, when the flux in the primary coil changes, where do you see the effect? Secondary, right? Flux was changed in primary, but you saw the effect eventually on the secondary, right? Yes. Take it right. When the flux in the primary coil changes, an EMF is developed in the secondary. When the flux in the primary coil changes, when the flux in the primary coil changes, an EMF is developed in the secondary. This phenomenon is called what? Mutual induction. This phenomenon is called mutual induction. When the flux in the primary coil changes, an EMF is developed in the secondary. This phenomenon is called mutual induction. And the EMF is called mutual induced EMF. The phenomenon is called mutual induction and the EMF is called mutual induced EMF. Okay. Now we'll go into a little bit of mathematics of this, then we'll take it for a break and come back. Okay, right. Close your book. I'll give you a few equations. Okay. Now I told you something. We learned this in self-induction. Look at this. The current increases. Tell me the sequence. Can you please tell me? Current increases. What happens then? Magnetic field increases. Then flux increases. Look at the reason. The reason is current. Look at the result. Flux. This is like a reason result equation or cause effect equation. Cause effect. This is the cause and that is the effect, right? Cause effect. All right. Okay, this is causing that. Anyway, I can say these are related. How? What kind of relation? Direct proportionality. Yeah, direct proportionality, right? Because when the current increases, field increases, flux increases. Current decreases, field decreases, flux decreases. So I would say flux is directly proportional to current. Correct. Direct proportionality. Yeah. So flux is equal to, how to remove the proportionality? Putting a constant L into I. This L is called self-inductance. It has a name, self-inductance. Look at this. Just like a resistor has a resistance, a capacitor has a capacitance, a coil always has a self-inductance. It's an inherent property of a coil. When you buy the coil has a coming pack. Understood? It is packed inside. It is like resistance for a resistor, capacitance for a capacitor. A coil always has a inductance. All right. Unit of inductance is Henry, which is abbreviated as H. All right. There is a CGS unit called absolute Henry. Absolute Henry. Okay, absolute Henry. But that is not used these days anyway. We have only Henry for the time being. Henry. All right. So this is self-inductance of a coil. Now let me ask you one thing. What was the equation for EMF? What was the equation for EMF we learned? Minus d phi by dt. Do you remember? E is equal to minus d phi by dt. Look at that. We learned it already. D phi by dt. So I am putting it now. That is equal to minus d by dt of what is phi? Can you tell me what phi is? EMF is what? Minus d phi by dt. That is d by dt of phi. What is phi here? Li. That's it. As simple as that. I'll get an L outside. It is a constant, huh?
Yeah.
L can be taken outside. So what we have now? E is equal to minus L taken out into di by dt. Got it? Is equal to minus L into di by dt. Based on which you have the numericals. Direct numericals only. Alright. EMF. First equation is this. Flux is given by L into I. Second equation is EMF is given by L into di by dt. Just like this, we can have mutual induction also. See this. Let us see the sequence. What is the sequence? What is the sequence? Tell me. Primary current increases. I must have said 100 times today. Tell me what? Primary current increases. Primary field, very good. Primary field increases. Primary flux increases. Secondary flux increases, right? So how are they related? 5 S's. Tell me, Bilal, when current increases, field increases, flux increases. Directly proportional, right? So I will say 5 S's. 5 S's directly proportional to IP. Primary current. This is the cause and that is the effect. Okay, 5 S is proportional to IP. Or I can say 5 S is equal to a constant into IP. Earlier I called it L. That was self-inductance. Then what must be this? Common sense will tell you. Tell me mutual inductance. Mutual inductance for a pair of coils. Mutual inductance for a pair of coils. Look at this. A resistor has a resistance. Capacitor has what? Capacitance. One coil has what? Self-inductance. Two coils together will have mutual inductance. Understood? Whenever you keep two coils side by side, they'll have a chance of mutually interacting, mutual inductance. Understood? Mutual inductance. Got it? And how do we write the EMF? EMF is minus d5 by dt. Correct? Correct.
Yeah.
So EMF in the secondary will be what? Minus d5 s by dt, right? So EMF in the secondary will be minus, minus d by dt of what is 5s? Same way we did. Look at this. Here I substituted for 5s Li. Here I am substitute for 5s as MIP. That's it. What is so complicated? MIP. I'll get the M outside. Okay. Okay. Minus EM into dIP by dt. This is EMF in the secondary. So for self-induction, we have two equations. Phi is equal to Li and E is equal to minus L into di by dt. For mutual inductance also, we have two equations. Phi s is equal to MIP and ES is equal to minus M into dIP by dt. Got it? Understood? So just write this down and take a break. All of you got it, everyone online? Just write it. Write heading self-inductance. 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 Okay. Self-inductance. Just draw the figure. This is the coil, and what is it called? What is it called? Solenoid, right? Solenoid, right? Yes. Okay. That particular shape is going to be called solenoid. Okay. Right. Okay. Now write this. Just write this. Current increases. Magnetic field increases. Flux increases. I must have said so many times now. Current increases, magnetic field increases, flux increases, right? So you can write. They are related how? Y is directly proportional to the more the current, the more the magnetic field. The more the field, the greater the flux. Correct. So flux is directly proportional to current. So flux is equal to a constant into I. Put these together in a box. That's a very important equation in fact. Okay. I promise you won't miss even half mark from this chapter. I think the weightage is 10 marks or 12. I promise. Just follow whatever I say in class. Okay. I promise. I'm 100% sure you won't lose even half mark. Okay. Phi is equal to Li. Where L has a name. What is the name of L? Self-inductance. Self-inductance. And what is the unit of self-inductance? Henry. Yes. Henry is the unit of self-inductance. Henry is the unit of self-inductance. Okay, so now you have what? Second equation. We will write the equation for EMF minus d phi by dt. What are you going to substitute? Minus d by dt of phi. Phi can be substituted Li. Phi is equal to L into Y. Clear, Nansha? Phi is equal to L into Y. Clear? Right. Phi is equal to L into Y. Right. Yes. So you can get this L outside minus L into di by dt. EMF is equal to minus L into di by dt. EMF is equal to minus L into di by dt. Okay. Clear. Similar way we will write, the other one will take. Okay. Mutual inductance. We did self. What is the difference between self and mutual? Self L, mutual M. That's it. You will replace all else with M's. That's it. Got it. One coil self, two coils mutual. Okay. Right. Okay, finish this. A formula like the BEB. BBL we did already. We did Kamal, but don't worry, we will revise it. That is called motional EMF. That part was done already, but I'll be doing it again, Kamal. Don't worry. Now write this mutual inductance. Mutual inductance. The same way you can proceed. Mutual inductance. Tell me, Rajat, what are you going to write? Primary current increases.
The unit for mutual inductance is also
Henry, say unit for mutual inductance also Henry. Okay. Rajat, do you hear me? Okay, right. So IP increases, BP increases, phi P increases, phi S increases. How do you say this? Tell me, Diti, what is this? This is primary current increases, primary field increases, primary flux increases, secondary flux increases. Did you hear me, Diti? Right. So how can you relate them? Phi S and IP are related, right? Like a cause effect relationship, like I told you already. Okay, fine. Thank you. So you can write phi S is proportional to IP. Phi S is equal to M into IP. Put this in a box. Phi is equal to M into IP. Okay. M is called what? M is called mutual inductance. Unit. Unit is Henry. Okay. Below which you can write the EMF. What is the equation for EMF? Minus d phi by dt. But since we are finding EMF in the secondary, you put S as the suffix. Okay. EMF is found in the secondary, right? Okay. Write this, that is equal to minus d phi dt of phi is what? Mi. Phi S. I can call it phi S. So ES is equal to minus M into dIP by dt. Minus M into dIP by dt. Okay. Minus M into dIP by dt. Got it? Okay, so we have learned self-induction, mutual induction, and I'll do one question. It's a derivation. Actually, there are 3 derivations in this chapter. We have 2 more to do now. Okay, these are important 3 more questions. Okay, I take a solenoid. I'm going to find out self-inductance of this solenoid. Look at this. This is the solenoid. I take a pipe, I take a pipe and I wind wires over it like this. I wind wires over it. Okay. So this is the solenoid I'm talking about. Okay. I have the solenoid. Mutual induction and mutual inductance. What is the difference between mutual induction and mutual inductance? Mutual induction is the phenomenon. Mutual inductance is the value. Okay, the value. Okay, mutual induction means that effect. That is called mutual induction. Mutual inductance is the amount, the value of mutual induction. Got it? That is called mutual inductance. It's also called coefficient of mutual induction. Okay. Mutual inductance is also called coefficient of mutual induction. Okay, I take a solenoid. What was the equation for phi? What was the equation for phi? Phi was written as L into I, right? Okay, now it's very easy. L is given by phi divided by I. Phi by I. Nothing. I just took this to denominator. And done. What is the equation for flux? Do you remember the equation for flux as D into A? No, forget about it. Do you remember the equation for electric flux as E into A? Again, forget about it. Flux is given by integral E dot ds. Do you remember this? Don't tell me that you have seen this. Okay, right. E into area is called electric flux. Similar way, magnetic flux is B into area. If there are n turns, it is NBA. For one winding, 1BA, two windings, 2BA, 3BA, n turns, NBA. So I put it here in place of phi, I put it NBA by I. And one last step, n into here now, A divided by I. What is missing here? Look at this, B. What is the value of B? That was learned in the last chapter. For a magnet, for a solenoid, the magnetic field is mu 0 n by n into I. Mu 0 n by n into I. Magnetic field of a solenoid. Okay, and I and I are cut. What are we left with? Magnetic field is given. So self-inductance is given by mu 0 n and n together n square area by L. You can stop here, but in school your teacher might not agree with this because in the reader they have gone one more step. Now tell me what you're going to do. This is mu 0 n square. I would rather write it as n into n. N square is n into n. Area by L, and I'm going to put an extra L. For compensating, I put an L here. Why am I doing this? Now this n by L is called number density. Number of turns per unit length. Number of turns per unit length. This n by L is also called number density. So what is it now finally? Mu 0. N by L is n. This n by L is also n. So n square AL. 100% sure in numericals you will have to use this equation. Okay, for derivation you can stop here, no problem. Not in your school exams. Your school exam you have to write until here. Understood? But for boards it's okay to stop here. Alright, it's not compulsory to go until here. But anyway, for numericals you will need to learn this equation. So in order to be on the safer side, it's better if we can learn this equation. Alright, mu 0 n square AL. Got it? Now this is for self-inductance. Similar way we will do for mutual inductance also. How are you going to do it? Phi is equal to mi and m will be phi by I. Same way we will proceed. Understood? Understood? We will get mu 0 ns np a by n. Why ns np? Secondary and primary. I can show you. Look at this. This is what I was talking about. This is my solenoid, the pipe, over which I am winding the primary. Look at the primary. Look at the primary. This is primary. Okay, primary coil. And where do we draw the secondary? Secondary coil I can draw above this. This is called the secondary. Got it? Coaxial winding. Primary and secondary. Got it? Number of turns is going to be called ns. For number of turns. Ns stands for what? Number of turns in? S for secondary. So ns must be what? Tell me this. The number of turns in secondary. NP is what? Number of turns in primary. Your teacher might take N1 and N2 because in textbook they are given N1 and N2. But I thought like it would be better to take NS and NP because we call them secondary and primary. Got it. Which one is secondary, which one is primary? There is nothing like that. You can call whichever you want as primary. The other must be secondary. Got it. Okay, secondary and primary. All right, primary, secondary. Okay, so let us write this. Start writing. Write reading self-inductance of. We will do it one more time. Don't worry. Self-inductance of. All of you already understood this. It's an important 3-mark derivation. One of the most repeated questions ever. Self-inductance of a solenoid. Self-inductance of a solenoid. All of you already understood this? Okay, so self-inductance of a solenoid. Okay, so you can write consider a solenoid. Consider a solenoid. Oh, refrigerate. Thank you, people. Voice. Consider a solenoid. Consider a solenoid of number of turns n. Number of turns TURNS. TURNS. Number of turns. Turn means winding. Okay. Consider a solenoid of number of turns TURNS. Turns n, comma area A. Number of turns n. Consider a solenoid of number of turns n, area A and length L, small letter L. Consider a solenoid of number of turns capital letter N, area capital letter A, length small letter L. Okay, next line. Flux is given by. Flux is given by. What is the equation for flux? Flux is given by phi is equal to, tell me what, L times I, right? Therefore, tell me what L is. Phi over I. Okay. All right. On the margin, you write phi. Phi is equal to what? This is coming from the last one. Okay. Phi is equal to NBA. For one turn, one coil, it is B into A. 2 coils, 2 into BA. 3 coils, 3 into BA. N turns it as N into BA. Right? NBA. So I can put it straight away to this. Phi is equal to L is equal to NBA by I. One more step, it is done. L is equal to N A by I. And what is this? Look at this magnetic field. Magnetic field, I'm going to substitute. What is the magnetic field equation? Mu 0 N by L into I. We learned this in the last chapter. Did you understand what I did? I started with flux is equal to L into I. What I want is L. L is phi divided by I. Phi is N B A by I. Correct? N as such, A as such, even I as such, and you are replacing B now. What is B? Give me your hands. Mu 0 N by L I. Cut those sides now. I and I are cut. Finally, you are getting what? L is equal to mu 0 N square. Why N square? N and N together, N square, right? Correct. In the area by L. Put this in a box. This is self-inductance of a solenoid. I'm not done yet. I'll modify this equation now. Self-inductance is mu 0 N square A divided by L. Okay. Also write this L is equal to mu 0. What is N square? N square is N into N. I'm splitting it as N into N. Okay. I'm making a slight modification. You know why I'm doing it, right? Because I said in the textbook they have done it. Okay. All right. So what am I going to do? I will put an extra L on numerator. But I can't do as I wish. If I do something, I have to compensate, right? I put an L on numerator. I put an L on denominator. Then N and L are taken together. N and L are taken together. What are they going to be called? Mu 0. This n by L, number of turns per length, that is called small letter n. It comes twice. So n square AL. That also in a box. That is an alternate equation, okay? Which is needed for solving numericals.
So you can't use the other one for solving.
Yeah, because in numericals, whenever they give, they'll give in terms of n only, small letter. So you'll have to use it. Understood? Number density. N by L is called number density. Number of turns per unit length. 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 Okay, now similar way. Hope it's clear, everyone. Okay, finished. Now mutual inductance also we will do. Now write again. Mutual inductance of. We found out self-inductance. Now it is mutual inductance of pair of coaxial. You know what it means? Coaxial means same axis. Coaxial. Coaxial solenoids. This is the primary coil. The yellow coil is the primary coil. Yellow coil is the primary coil. And the green one is the secondary coil. Primary and secondary are wound over each other. One is wound on the other. Mutual inductance of a pair of coaxial solenoids. You don't have any other types of solenoid. If you choose to learn electrical engineering, in semester 3, you will have a paper called electrical technology where you will learn other types of solenoids. But here you have only coaxial solenoids. Okay, coaxial solenoid, same axis. Okay, coaxial solenoids. We can write consider a pair of consider a pair of coaxial solenoids with the number of turns ns and nd. Consider a pair of coaxial solenoids. Consider a pair of coaxial solenoids with the number of turns ns and np. Okay. Okay. Next line, flux is given by. You can proceed the same way we did in the last case. Flux is given by. Flux is given by phi s. Phi s is equal to MIP. What you need is M. So take the other guy to the left hand side. M is equal to phi s by IP. M is equal to phi s by IP. Hear me again. Phi s is given by. Phi s is given by. Tell me, phi s is given by MIP. M is equal to phi s divided by IP. What are you going to substitute for phi? Phi, do you remember? NBA. Okay. So what will be phi s? Hear me please. Phi s. NS. BS. No. It can't be BS. Because secondary does not have field. Who has the field? Primary alone has the field, right? So you have to put BP there. Got it? Got it. Who alone has field? Only primary has cell. Only primary has current. Only primary has field. primary field is taken by secondary, right? Correct. So primary has field. I repeat one more time. You will have a tendency to write phi s as NS BS AS, but that's wrong. NS BP should be used because magnetic field belongs to what? Originally belongs to primary, right? Magnetic field is that of primary. Secondary does not have its own magnetic field, right? Into AS. So let us put it here. M is equal to NS BP AS divided by IP. One last step. We will do M is equal to NS AS divided by IP in bracket. We will substitute the magnetic field, right? Correct. Just like we did before. Correct. What is the magnetic field? Mu 0 N by L into I. Say it again. Mu 0 N by L into I. So mu 0 NP by L into IP, because I am talking about primary. That is why I put the suffix P. Even for L you can put P, but it is not essential. Okay. So cut IP. What do we get finally? M is equal to, let you go in 2 minutes. Mu 0 NSNP AS by L. You can stop here like I promised, but the problem is school won't. Okay, mu 0 NS NP AS by L. You're going to introduce an L here. Compensate by putting L here.
It won't be an extra.
No, you take those two here.
Yeah, that's a
NS. This will be NP. Got it. Finally, we have like what? M is equal to mu 0 NS NP AS into L. Mu 0 NS NP AS into L. I'll explain one more time and then wind up, okay? These two derivations are very important. They have come many times in examinations. You can check it yourself to see if I'm lying. Okay. Okay, I'll just explain one more time in 1 minute. So tell me when you're done. Finished. Somebody online. Okay. Alright, okay, thank you. Right, see this? Now this is about mutual inductance. We have a pair of coaxial solenoids. Coaxial means both the coils are wound over the same coil, right? You take a pipe like this, wind one wire, over which you will wind another wire. I'll show the actual device in the next class. Okay, right. So, and then what? Flux is given by M into IP. I want M, so M will be phi s divided by IP. What is flux? NBA. But remember, NS BP into AS because field is primary field. So NS BP AS by IP. I'm substituting for BP here. NS mu 0 NP IP by L. Magnetic field is given by mu 0 N by L into I into AS by IP. You see, IP cut. You get mu 0 NS NP AS by L. That is the final equation. NS is number of turns in secondary, NP is number of turns in primary. And then what are you going to do? You will introduce an L here, and for compensating, you put an L here. NS by L. Number by length is called number density. NS by L is called small letter NS. NP by L is called small letter NP. NS is called number density of secondary. NP is called number density of primary. So finally, the equation is mu 0 NS NP AS into L. Got it? So in this chapter, what remains is a small derivation, energy stored in an inductor. Okay, so I'll finish it and I'll do a revision of this chapter. All right, then we'll switch to the next chapter. Okay, so shall we wind up for the day?